Assalamualaikum and hi everyone. Today we're going to learn about the Cauchy-Riemann's equation, which provide a necessary and sufficient condition for a function fz to be analytic in some region of the complex plane. This allows us to find the first derivative in that region. Here we will go through 5 examples related to the Cauchy-Riemann's equation to understand the idea of a complex function and its derivative. A complex function fz will depend on x and y respectively and written as fz equals to u plus iv in terms of x and y. Finding the derivative can be complicated. Therefore, Cauchy-Riemann developed theorem to determine derivative of a complex function. We note that there is a very useful test to determine whether a function is analytic at a point based on these two conditions, which is if and only if a partial derivative of ux equals to a partial derivative of vy and partial derivative uy equals to negative partial derivative of vx. The use of if and only if means that if the equations are valid, then the function is differentiable and vice versa. Here is the first example for a function gz, and we will have to find its derivative and then compute g prime for 2 plus I if it exists. Firstly, we need to extract the function given, gz, and then from that function, we will set the u in terms of xy and also v in terms of xy. The second step is to do a partial derivative of ux and then partial derivative of uy. Same goes for vx and vy. Therefore, we will consider those two conditions that previously stated, ux equals to vy and uy equals to negative vx. From the value that we've computed, we can clearly see that CR equations are satisfied. We can conclude that gz is analytic on the whole complex plane. Therefore, gz is entire. So, the required derivative is gz equals to ux plus I vx, which is equals to 3x squared minus 3y squared plus 6xyi. We can also get the derivative from vy minus iuy. So, to compute g prime 2 plus I, we will have to substitute in the equation of the first derivative with the value of x equals to 2 and y equals to 1. Therefore, you will get 9 plus 12i. Here in example number 2, we have a function of fz equals to x squared plus iy squared, and we have to determine whether this function is differentiable and what is the region of analyticity for f, and to compute f prime for negative 20 minus 20i and f prime 1 minus I if possible. So firstly, we have the function, and then we extract from this function given u component, which is equals to x squared, and the partial derivative for ux is 2x, partial derivative for uy equals to 0, and then we do the same for v component, where we have partial derivative vy equals to 2y and partial derivative vx equals to 0. So here we can see the Cauchy-Riemann equations are satisfied when only if y equals to x, because we have ux equals to 2x and vy equals to 2y. Based on the Cauchy-Riemann's equation, we should have ux equals to vy. In order for us to have ux equals to vy in this case is when y equals to x. So f is differentiable at each point z equals to x plus iy on the line y equals to x. Therefore, f is nowhere analytic. So the required derivative if f prime z equals to ux plus I vx, which is equals to 2x. We can also get the f prime z from vy minus I uy. Since negative 20 minus 20i is on the line y equals to x, which is y and x equals to 20, therefore we can find the first derivative of that function is a negative 40. However, for f prime 1 minus I, it does not exist since 1 minus I is off the line y equals to x, because x equals to 1 and y equals to negative 1. Next, we have example 3 to show that the function fz equals to z cubed is analytic everywhere and hence obtain its derivative. So to start with this function is to replace z with x plus iy cubed, and then we get the function in terms of u plus vi. Then we extract the x component and find the partial derivative ux, also uy. The same goes for v component, for partial derivative vy and vx. We can simply conclude that ux equals to vy and uy equals to negative vx, where these CR equations are identically true, and then we can conclude that fz is analytic everywhere. So the next question is to obtain its derivative for that function. We obtain the derivative of that function using ux plus vxi, which is equivalent to 3z cubed. Next, example 4, show that if fz equals to zz conjugate, then f prime z exists only at z equals to 0. From fz equals to zz conjugate, we get x squared plus y squared. Then from that complex function, we have only u component, which is x squared plus y squared. And finding partial derivative for ux is equals to 2x and partial derivative for uy equals to 2y. So here v component is equals to 0, therefore vy and vx equals to 0. So in this case, we can say that CR equation are satisfied only when x equals to 0 and y equals to 0. Here, in this case, we can have z equals to 0. We can conclude that fz is not analytic everywhere. Example number 5 is show that the function fz equals to z squared plus z is analytic everywhere and hence obtain its derivative. What we do is, again, we substitute x plus iy in z squared plus z. From here, we extract the u component and y component in terms of x and y. Then only we can get the partial derivative of ux and uy. For v, we have vy equals to 2x plus y, which is equals to ux. And then for vx, we have negative 2y, which is equals to negative uy. So we can conclude that CR equations are identically true, and hence fz is analytic everywhere. The first derivative of fz is using ux plus vxi. We have 2z plus 1. Here are some exercises that you can practice to strengthen your understanding about Cauchy-Riemann's equation and complex function derivative.